Hi, and welcome to this webinar with the title Discovering the Geometric Suite of Data Analytics Solutions. This webinar is number 5 in a series of 11 webinars aimed at exploiting the data analytics capabilities of the Geometric Suite, and this session has the subtitle Centering and Scaling, When Not, and When May Be. On this slide, we see an overview of the Geometric Suite and all the solutions that are part of the suite. We have the model software for design of experiments and quality by design. And this software was addressed in webinars 1 and 2 in this series. We have Easy Analytics for enabling everyday data-driven decisions in an efficient way. And this software was discussed and exemplified in webinar number 3. Here we have the SIMCA software for multivariate data analysis, and this is the software with which we will be concerned today. We have the SIMCA online software for deploying models developed in the SIMCA software in an online scenario. Beyond the SIMCA online, we also have the control advisor for advised predictions into the future. And finally, we have the active dashboard solution for enabling an overview of many models in the online setting, perhaps deployed at different sites or different geographical locations. In webinar 4, the just preceding webinar, we started to scratch on the surface of what multivariate data analysis is, and today we're going to zoom into pre-processing tools that will help us to improve our models and enable models with an improved interpretation and also usefulness. So we have a little introduction first. We will discuss transformations as an important part in pre-processing. We will look into centering and scaling, when to scale and when not to scale, and when maybe, as was alluded to in the title. We then have 2 examples. The first example is where the recommended scaling would be no pre-processing at all. And the second example is a spectral example that we will use to illustrate, contrast, compare centering, Pareto scaling, and unit variance scaling. And it is the second example that will also be demonstrated in the demo part using the SIMCA software. And after that, there is a summary and conclusion towards the end. So as an introduction to this presentation, we can say that raw data analysis is important, and if done carefully, the subsequent data analytics may run a lot smoother. And raw data analysis and visualization is done in order to get a better feeling for the data, for finding out regularities and peculiarities in the data, and also to understand and perhaps remove anomalies if they exist. And part of the raw data analysis involves assessing and understanding appropriate pretreatments of data to find out if they are needed or not needed. And I think it's fair to say that pretreatment of measured data is carried out in order to reshape or transmute the data in order to facilitate the ensuing data analysis and model interpretation. And depending on the application area and the problem at hand, different pre-processing tools are used, and often in different combinations. Some of the most often used pre-processing steps involves spectral filtering, denoising, and compression. Transformation, using, for instance, the logarithmic transformation or perhaps the square root transformation, and centering and scaling. And regarding centering and scaling, there are also advanced extensions, for instance, advanced scaling and battery scaling. In this presentation, we're going to zoom in particularly on centering and scaling and some of the options that are available in the SIMCA software. And regarding centering and scaling, there are a couple of influential parameters which will have a great impact on the outcome of the pre-processing. And here I'm thinking of mean values and standard deviations of the variables relating to the columns of the data table. It is important that the mean values and standard deviations are representative of the properties and structure of the data, and they should not be influenced or perturbed by outliers or strange or unreasonable measurements. If the standard deviations and mean values are not representative of the data, there is a risk that errors are propagated into the preprocessed data. And in this respect, we then have the trimming and winsorizing procedures which are available in the SIMCA software for accomplishing robust estimates of mean values and standard deviations. The trimming and winsorizing procedures are perhaps not in focus in this presentation, but they provide a means to remove extreme or unreasonable measured values from the data and either replace these values by some good guesses, some good alternative values, or simply just leaving blank cells or missing data in the data table. SIMCA offers a quick info functionality by which properties of the imported data can be visualized, numerical summarized, and inspected. And the quick info is a configurable docking pane that provides basic statistics and plots for a column or a row. And on this slide, we see the observation mode, which is useful when working with spectra. So the basic plots relates to a frequency histogram, a spectrum, and the power spectrum. And there are a number of different univariate statistics that can be called upon. There will also be a sliding selection bar to help us quickly navigate between the rows. So either we can drag this navigation bar left, right, or we can use the arrow keys to go up and down in this table. The alternative mode is then the variable mode, which is useful when working with process data or data that are acquired with a strong time dependence in them. And we then have similar sets of default plots. We have the frequency histogram, but when we are working with variables, we also have the line plot of the time series and then the autocorrelation plot. And regarding the pre-processing steps that we're going to address in this webinar, some very basic input is provided by the quick info functionality when run in the variable mode. And here I'm thinking about the histogram, which visualizes the distribution of a response. And I'm also referring to the trim wins entries that can be used to pre-process the data before calculating averages and standard deviations. One important thing to consider in data pre-processing relates to transformations. To the left here we see a histogram of a variable where we have a very sharp tail to the right. It means that this variable has a number of measurements that are numerically much larger than the bulk of the measurements for this variable. So we have a skew distribution. In the right-hand histogram we see data or the situation for the same variable after log transformation. And here the distribution is a lot closer to an approximate normal distribution, and that will then lead forward to a higher efficiency in the data analysis. And in general, if the data are not approximately normally distributed, a suitable transformation may be required to improve the modeling results. The quick info in the variable mode also provides these mean values and standard deviations that are the essential parameters regarding centering and scaling. On this slide, we are exemplifying another important step in the pre-processing of data, and this relates to scaling. And the problem here is that variables can have substantially different numerical ranges. The data table that we see here is drawn from our tutorial example called LooWarp. The details of the application is not really interesting or critical at this stage, but what we are zooming into are the two variables that are rendered against the green background. We have one variable called WRP3, which has a numerical range between 0.2 and 1.0, and we have another variable, another response called ST4 that numerically varies between 17,000 and 30,000. Now, unless we are doing anything to correct or compensate for this difference in numerical ranges, any data analytics tool existing within the SIMCA software will automatically zoom into and try to capture the variation in this variable because it represents the variable with the largest variance. It is the largest source of variance. There is an equivalence between the initial variance of a variable and its length, and that means that we can interpret ST4 as a very long variable. It has a large initial variance, and we can interpret WRP3 as a very short variable because it has a small initial variance. And on the next slide, we're going to compare the effects of analyzing data as they stand here right now without any compensation for the different numerical ranges, as opposed to taking some corrective measures into account for balancing the information content in the two variables. So on the next slide, what we are seeing are two loading plots arising from two alternative models. In the left-hand part, we are looking at the result after scaling all variables to unit variance, meaning that all variables have the same initial variance. All variables seem to be seen by the model, and here we see where we have ST4 and WRP3. On the right-hand side, we have a loading plot that would arise if we would not do any standardization of the data table and just apply the latent variable modeling directly to the table of the previous slide. Then the information that we see is that the model is dominated by just a few of the variables, ST2 and ST4, for instance, which are the variables with the largest initial variables, the longest variables. So scaling to unit variance is a way to decrease the in-model influence on variables that have a large numerical variation and make it possible to see variation also in variables that have a smaller numerical variation. Another little example just to make the point. This example deals with the body height and body weight for 23 individuals. It is 22 players and a referee in a pre-season friendly football match where these measurements were registered. If we start with the right-hand plot here, we're seeing a scatter graph between body weight and body height. And here we see that 30 units of body height in meters occupy the same distance as 30 units of the body weight in kilogram. And when we have that sort of representation, we're using the same scale for the two variables. We will see that we have one long variable, which is body weight, and one short variable, which is body height. And basically what we are seeing is only the information in the long variable. We can say that the quote-unquote model, which is the scatter plot in this case, only captures the information in the long variable. Alternatively, if we instead of plotting the data using the same scale but are plotting the data according to the principle of the same spread, we start to see much more interesting things. So in this alternative plot seen on the left-hand side, we're plotting body height such that the 30 points occupy the same distance as the 30 points of the body weight do. So we're plotting according to the same spread. First of all, we see that there is a relationship between body weight and body height, meaning that generally when the person gets taller, the weight is also increasing, except for one atypical person, which breaks this correlation structure. So we see, in addition to the relationship between body weight and body height, also an atypical person. And that is the individual for which the data are boxed here in the table. And it is the referee in the game in this case. So depending on how we're pre-processing the data, we may facilitate the possibilities to detect interesting information in the data. And clearly in this case, plotting the data and viewing the data according to the principle of the same spread makes it possible to conclude that there is a strong relationship between body height and body weight, and we also diagnose an outlier. And that information is not at all so easy to reveal if we instead are watching the data according to the principle of the same scale. So then unit variance scaling, what is it, how do we accomplish it, and what effect does it have on the data? First of all, the basic condition for considering or finding UE scaling relevant is that variables are different in nature. They are generated by different underlying generating mechanisms, often resulted in large spread in the numerical ranges. So if variables are measured in different units and there are large differences in as far as their numerical ranges are concerned, data are scaled to give each variable an equal chance to influence the model. And what we are doing is that we will, for every column in the data set, calculate, in addition to the mean value, also the column-wise standard deviation. So the unit variance scaling in the column-wise implementation means that first of all, for every column, we will subtract the column mean value and then divide by the column-wise standard deviation. The result of that is that all variables that are scaled according to this principle get a variance of 1 unit variance. Here we have tried to graphically depict what the UV scaling is doing. So every yellow bar here should be interpreted as a variable. Some variables have a large numerical range corresponding to a large initial variation. Some variables have smaller numerical ranges corresponding to smaller initial numerical variances. So what we are accomplishing, the effect we're accomplishing with UV scaling is that the long variables are a bit compressed and the short variables are stretched out, such that after the scaling they are all on a comparable footing, variance 1 unit variance. However, if the variables are measured on the same scale, data are generally only centered, and this applies, for instance, to spectral data. Spectral variables have the same underlying generating mechanism behind them, and therefore there is information in variations in the signal amplitudes. So for that reason, the spectral data are usually only centered. But we will come back to that in the second data set, where we will compare the effect of unit variance scaling and centering. Now, another scenario is as follows. We are now going to discuss something called Pareto scaling. When we are working with spectral data, for instance, NMR data, there can be large peaks, but there can also be intermediately sized or medium-sized peaks, which definitely contain information. So what would happen if big features dominate, but we also know that the medium features are important? Well, then there are two risks with the techniques that we discussed on the previous slide. Centering only, here the risk is that the centering only would mean that the large peak will dominate, and the risk is that the medium peaks will then be masked by the large peaks. Using unit variance scaling and mean centering would then mean that we would penalize the large peaks, and the risk is then that we may blow up noisy regions, for instance, inflate the baseline noise. As a way to balance these two risks, we have devised an alternative scaling called Pareto scaling. So Pareto scaling is in between centering only and mean centering and unit variance. And what we're doing here is that instead of dividing the mean centered values with the column-wise standard deviations, we are dividing the mean centered variables with the square root of the column-wise standard deviations. So this means that we will weight up medium features without risking to inflate the baseline noise too much. And this Pareto scaling is the recommended option when you're working with metabonomics data and also some type of proteomics data. As you will see in other webinars in this series of complementary webinars, we also have other user interfaces in the SIMCA software apart from the default user interface. We call these modified graphical user interfaces for skins. And using skins means we also have a possibility to change default settings when doing the data analysis. So if you're running something called the omics skin, and there is a webinar on the omics skin, then the default pre-processing of the variables would usually be Pareto scaling. And if you're running the spectral skin for spectroscopic data, and there is also a webinar on the spectroscopy skin, then the default setting regarding centering and scaling would be mean centering only. Now we're going to look into the first of two examples where no scaling at all is the recommended option. So neither scaling nor centering, and the notation used in the SIMCA software would be none. The background to this data set is that the data reflect or relate to quality control of polymer disks. And these polymer disks are then to be used inside electronic devices. You can think of this polymer disk as similar to a coin, and the property of interest is the thickness of the coin. So there are 9 sensors that are spread out like this across the surface of the coin that are measuring the thickness. So we have one thickness measurement center in the interior part of the coins. We have then a middle circular array, and then we have also a couple of sensors in the peripheral part of the coin. And here we see the coin from the side, and each coin then has a certain target thickness. There is a specification as far as how thick the polymer disc would be. And the problem here, or the objective, was to produce discs with a uniform thickness within a given specification. The problem for this manufacturer of the polymer discs stemmed from the fact that there was a small but very expensive increase in the number of rejected discs. The data set we have then the 9 thickness measurements as variables, and then we have 184 polymer discs, 184 rows in the data table. Now, because there is a target specification, a given thickness, the data are not given as the absolute thickness measurements, but they have been standardized in relation to the target thickness. So the data table that we are analyzing contains data where each thickness measurement has been from each thickness measurement, we have subtracted the specification. So the data table contains data that are corrected for the target thickness. So if in the data table you would have a row with only zeros, then you would have a polymer disc with the ideal thickness. So the data are given as deviations from target, and here we see that there are small numerical differences from 0, meaning that this polymer disc is close to the target thickness. If we would have only positive values, it would mean that there is a polymer disc that is slightly larger than the specification. And if we correspondingly would have only negative values, then we would have a polymer disc being slightly thinner than the target thickness. So because all variables are of the same type, we would not consider scaling, and because the data are given as deviations from the target, we would not consider any further centering, because any additional centering would remove the diagnostic effect we are after of having the target at the center of the score plot. So that is why the recommended scaling option in this case is none. The variables are of the same type, no scaling, and they are already centered with regards to the deviation. They are already centered with regards to the target thickness. On the next slide, we see the resulting plot coming out of the initial PCA model. And because we have now used scaling equal none, it means that if we have any polymer disk at the origin of the score plot, that would be a polymer disk of the ideal thickness. And that means that the closer we are to the origin, the more closely we are to fulfilling the target thickness profile. If we would have mean centered the data using the grand average, we would have removed this diagnostic effect. And then if we would have mean centered the data, we would have moved the 0, 0 coordinate to be somewhere here where I'm pointing right now. Then the origin of the score plot would coincide with the center of gravity of the entire point cloud. There would be a small shifting. So in this case, scaling none is the preferred choice, because then we have the diagnostic upside of interpreting what the origin of the score plot would mean. The second example is a spectral example. And we are going to compare centering, Pareto scaling, and UV scaling and see what effect it has. So this is another tutorial data set. It deals with the spectroscopic characterization of strong liquors. And we have this data set. It's called distilled liquors in our compilation of tutorial examples, so you may have come across it. There are 46 unique samples corresponding to different beverages. Four of these beverages have been sampled twice, so we have a couple of replicates, giving a total of 50 observations, 50 rows in the data table. And these products relate to bourbon and brandy, cognac, single malt and blended malt, and also some rum. And we also know the country of origin for each of individual beverage. And for each sample, data in the range from 200 to 600 nanometer was acquired. And due to the resolution used, it meant that 108 variables were available. And we will now use this data set and investigate the effect of scaling. So here we see line plots of the original spectra. So the 4 plots on this slide show the data prior to and after the different scaling approaches. And we can see that the spectral variation is most pronounced between 200 and 350 nanometer, and essentially above 450 nanometer or so, there is nothing but major baseline variation. We have one spectrum here that is shown as a thickened black line. It has a thick black line in all plots. This is a little atypical spectrum, and it is arising from a rum sample. It is the only rum. It is a Japanese product. If we are using unit variance scaling of the data, meaning that we are compressing the peak and augmenting the baseline variability region, we can see how this spectrum stands out after UV scaling. So the ability or the risk of UV scaling to blow up noisy regions is evident in this plot, and it also this sort of scaling would also emphasize the deviating properties of the Japanese rum. This atypical spectrum is a little less extreme if we Pareto scale the data, and with this scaling there is still some scope for the high wavelength region to impact the analysis, but definitely the peak will dominate. In the last example, we are just plotting the spectra after centering, and now we see that the Japanese rum actually conform a little better to the other spectra using only centering. So its extreme character has been decreased a bit, you can say. But the main conclusion in looking at these plots is that above 450 nanometer or so, there is essentially no structure in the data. It's just baseline variability. And this is also the example that we're going to demonstrate inside the SIMCA software. And I will show you how you can modify the scalings and plot the data and visualize the changes and impacts of the different scalings. So speaking about this brings us to the demonstration. So I will now swap over to the SIMCA software and just in just a while continue with the demonstration. And I will now continue a bit on where we stopped in the previous webinar in the demonstration parts. If you want to know the basic architecture and mindset of the SIMCA software, please look at the recording of webinar 4. We are going to create a regular project. We will locate the data file, and always when we import data into SIMCA, it will need at least one primary identifier for the row and one primary identifier for all the columns. The primary identifier for the columns is simply the nanometer for each variable in the span 200 to 600 nanometers, separated by 0.5 nanometer. We have a couple of additional secondary identifiers representing country, representing product, and representing whether a certain sample is a replicate or not a replicate. And then we also have a composite index, just to indicate that possibility that you can combine indices also. The issues pane reports no problems, so we can finish the import. And when we do that, I was clicking on the wrong button, sorry for that. We overwrite, I did a rehearsal this morning, so we're just overwriting that project file. Now we're inside the SIMCA software. We can look at the data table just to see that the import seems to have proceeded or performed the actions we expected it to do. It has recognized all the identifiers. We can also plot the data by using the Spectral button. And here we see the 50 spectra across the entire wavelength region from 250 up to 600 nanometers. Because we have a number of identifiers, we can always use that information for coloring. We can color, for instance, according to product. And if we combine that with also selecting the highlight series tool, we can hover on a certain level or label in this legend. So here we see all the blended whiskies, the bourbons, they seem to have a higher absorption. We have a couple of brandies, we have the cognac, we have a mixture sample that is made up of several of the different whiskies that were there, just mixed by the students. We have the Japanese rum that was standing out substantially, and we have the single malts. And if you start to compare, you will see that there are some differences between the single malts and the blended. So in this classification type exercise, my gut feeling is that you would be able to tell, for instance, single malt apart from the blended ones using these data. We can also color by other IDs, for instance, the country. We have just one sample from Canada. It is a single malt. Then we have the French cognac. We have the information on Ireland. Italy is just one sample. Japan, well, that is the rum. We have Scotland and the US. So we can go on and use different kind of colorings in just by looking at the raw data and thereby extract very interesting prior information, prior even to building a model. We will now use the tool that is called Principal Component Analysis that was introduced in the webinar 4 and make a summary of the variation in this data set. We will calculate 2 summary indices or what we also say 2 principal components, and we can see that these 2 summary indices or components are very efficient in explaining the spectral variation among these 50 observations, and with these 2 components, as we say, we account for 97% of the variability in the data. If we plot the scores, then we see each spectrum as a point, and points that are close together are very similar, and points that are far away are then more different. I will turn off the number. It doesn't really make much sense in this case. We will then plot and color by product, for instance, and again we have a similar possibility. We can highlight where we have the single malts or the blended whiskies, and we also see that the Japanese rum is standing out. We can go on and color by other IDs, and one ID that I didn't use in combination with the line plots of the spectra was the replicate index. But now it's very interesting to use the replicate index when we have the score plot, because we now see where we have the replicated samples. And in this case we have very encouraging or useful insights coming out of the replicate index. We can see that the 4 pairs of replicated samples are very close to each other, which is of course encouraging. It would have been much worse if the replicated experiments would have spread much larger and perhaps have a spread among the replicates that is in parallel with the spread across the whole score plot. In this case, we have a very good situation, and it indicates that we have good quality in our data. The variation among the replicates is much smaller than the variation across the entire data set. That is what I'm trying to say. We can go back and just have the default coloring. Now we are going to investigate also the influence of other scaling types, but I will first of all, before we do that, give you a little trick of how to handle information and documentation, and that is by using the title, changing title possibility. So I'm right-clicking and I will change the title, and it will read UV scaling here, like that. And if I then create the score plot again, that information will instantaneously be visible in the top part of the plot in question. Now, in order to modify the scaling, we will have to go into a dialog called the workset dialog, and I did a little walkthrough of this dialog in connection with an earlier webinar. So I will not repeat that here, but we will go to the scaling tab, and we will modify the scaling for all variables, modifying the scaling type from unit variance scaling to Pareto scaling. We can also select centering only here, or the none option that I also mentioned in connection with the coin dataset. So we take Pareto scaling, we are clicking set, the type column is changing, so we get a verification that the changed scaling has been recognized. We click OK, and we have now prepared for calculating an alternative principal component analysis model, now based on the Pareto scaled data. So I will now use that possibility to modify the model title, and I will type in Pareto scaling like that, and I will create the alternative score plot like that, and we tile them side by side. And here we have the Japanese rum sample that I am now highlighting. So if we start by interpreting or looking at the first principal component score vector in the case of unit variance scaling only, we can see that the first component models 66% of the variability in the spectral measurements, and this first principal component is very, very much influenced by this deviating or extreme property of the Japanese rum. The first component is aligning a lot towards explaining that sample. If you're using Pareto scaling, on the other hand, we can see that the Japanese rum sample has come much closer to the other samples. It means that more samples are coming into play, or being better seen in the model. You can see now that there is an increase in almost 20% of the explained variance for the first component. It's close to 86%. It's increasing from 66 to 86%, and that strongly indicates that the first component sees much more variation than just the Japanese rum. We can now continue and also make a similar modification and view the influence or the impact of just centering the data. And I will now, like a good chef, I have prepared an alternative SIMCA investigation file where I have arranged everything. So in the left-hand part we have the UV scaling. In the middle segment we see the Pareto scaling, and then in the right-hand side we see now the centering. And when we're using the centering option, we see that even more variability is accounted for by the first principal component. It's now up to 92%. So the interpretation is that going from unit variance scaling over to Pareto scaling and finally centering means that we have weakening the impact or the influence on the model of the Japanese RAM more and more. And when we have the centering only, we have a better chance to see the variation in all the other samples. Now, of course, we can also have a discussion around whether the Japanese RAM at all should be in the model. Maybe it is so much different from all the other samples that it should be regarded as an outlier and simply be discarded from the model. That's another possibility, but what I wanted to show you here is that sometimes you can accommodate samples that are deviating or on the border of being an outlier by modifying the scaling. And in this case, the sequence of going from unit variance scaling in the left-hand part, Pareto scaling, over to centering only is one way to accommodate the Japanese RAM. It gets less and less influential. Another perspective is given by the lower triplet of plots. Here we have the loading spectrum of the first principal component in each case. Here we have the first loading spectrum using unit variance scaling. Here we have the first loading spectrum using Pareto scaling, and here we have the similar thing after centering. Now, one thing that is always desirable is if the loading spectrum of the different components can be linked to spectral features, spectral characteristics, because that will help us to interpret and figure out a physical-chemical meaning, perhaps, to the meaning of the different components. We can actually also make another plot here where we plot these loading spectra together. We change to observation and loadings. We want the variable ID, and then we enter the loading of the unit variance scale data. We enter the loading of Pareto scaled and centered scaled, and we can also actually add the variable, the average spectrum, like that. So here we have and then we should also have the highlight series on. So here we have a plot where we have the loading spectrum. In the same plot, we have the loading spectrum that arises when we have unit variance scaling, and you can see it does not at all reflect the properties of the original data. We have the first loading spectrum arising using Pareto scaling. We have the first loading spectrum after just mean centering, and here we have the average spectrum. And this is something that you often expect, that if you're working with central data only, the profile of the first loading spectrum should be very similar to the average spectrum, and if that is the case, it is very easy to interpret the meaning of the first principal component. So in this case, due to the similarity of the loading spectrum after centering only with the average spectrum, that would tend to point in favor of using the centering in this case, not only because it helped us to accommodate the strange behavior of the Japanese RAM better, it also gives an easier interpretation. So now that we have seen how SIMCA can work with this spectral data set, we are going back into the PowerPoint, and we'll just round off with a few final statements. So the objective, you can say, with the geometric suite of data analytics solutions is to help our users and clients to see what others don't. We have, as I told you, the model software for DOE and QBD. We have Easy Analytics for everyday data-driven decisions, SIMCA for multivariate data analysis, SIMCA Online for real-time application of the multivariate models developed in SIMCA, the Control Advisor as an optimization and future-going addition on top of SIMCA Online, and the Active Dashboard as a final top layer to collect and visualize data from multiple SIMCA Online installations. Now, removing the names of the software but preserving the structure of the geometric suite, we can say that the tool set that we have in our suite that will help us to see, that will help our clients to see what others don't. They will do that in terms of addressing 4 essential or central data analytics questions or data analytics stages. To the right, we have what we can say the 2 reactive stages of descriptive data analytics and diagnostic data analytics. With the descriptive stage, we want to find out what has happened in the past. The diagnostic stage, we want to understand why a certain thing happened. And then in the left-hand part of the slide, we have the more proactive stages of data analytics relating to the predictive question and the prescriptive question. In the predictive scenario, we are trying to figure out if we would change certain things, and we then want to understand what could possibly happen in the future. In the prescriptive stage, we are instead rephrasing the question and trying to figure out what should we do in order to make a certain outcome happen, or perhaps even more importantly, what should we do, how should we act to avoid an issue to happen. And we will come back to all these questions also in the remaining 6 webinars in this series of 11 webinars. But for now, this is enough. And I will just round off by saying that the geometric suite is there to help the users and clients to analyze the data, to find the golden nuggets, to understand how to capitalize on these golden nuggets, and thereby understand how to change a little in their production, and through that, such measures grow a lot. So with these words, I thank you for your attention, and I hope to see you on board sometime in the future when we continue our walk through the different capabilities of the geometrics suite. Thank you and goodbye.